Okay. So let me close the door. And please accept my apologies. I need to keep the phone turned on. Hopefully it will not ring. Okay. If it rings, we will take 1 minute break. Okay. So, last time we got more or less here. I'm on model. Perfect. And there is a formula here that you cannot see now, but it's not a problem. I will move the slide later on. Okay, so we're talking about Rey-Foronov modeling, as you remember, and we are talking about this model. And I already introduced the basic concept to you, which is the fact that the model assumes that if you have a given catchment, remember the definition of catchment, which conveys water to a river cross section, which is the closure. We assume within this catchment that each location, and this is the location I, for instance, I indicate it with the I, each location is characterized by a capability of soil to store water. And we assume that this capability to store water is variable in the catchment. But as I said, we don't want to describe where the catchment has a given soil water storage capacity C star. I indicate the storage with C, and C star is a generic storage. I don't want to describe where I have a given storage C star. I just want to describe for each value of C star the probability that in the catchment a random location has a storage that is lower than C star. So the probability is the frequency, as I said. So I introduce a probability function, f, correct, C star, by definition of probability, f is varying between 0 and 1. We are not recalling the definition of probability, but I mentioned to you that probability, we interpret it as a synonym of frequency. So frequency is between 0 and 1, okay? Probability by definition is defined between 0 and 1. We don't recall, as I said, definitions of probability. But basically this f C star is a probability distribution, a probability function, which varies between 0 and 1. What is f, capital F? Again, I repeat, it's the frequency, probability, with which in the catchment I find locations where storage is lower than C star. So if I say that f C star is equal to 1, the maximum, it means that in the catchment, everywhere, I find a storage that is lower than C star. Okay? Storage usually is expressed in millimeters for a soil. It's storage per unit area. So typically, C is expressed in millimeter. And order of magnitude can be between 0. Of course, if a soil is impervious, the potential water storage is 0, up to 300 millimeters. It's a huge storage. It's a huge potential storage. So as I said, if I take a storage like C star equal to 200 millimeters, and I say that F in the catchment, F of 200 millimeters is 1, It means that everywhere in the catchment I have a storage that is lower than 200 millimeters. If I say that f of, let's say, 10 millimeters is 1, it means that everywhere in the, is 0. It means that everywhere in the catchment I have a storage that is higher than 10. So this is the meaning of f. It's a frequency with which, again, I find in the catchment a storage that is lower than C star. Okay? So this is a probabilistic description. If I am able to write this probability distribution function in mathematical term, this gives to me an opportunity, as we will see, to compute the runoff production in the catchment. Because I assume that if it rains, and it rains where the catchment cannot absorb more rain, then runoff is produced. The model works in this way. Basically, the model looks at rainfall over the catchment and assumes that where, again, it rains and the storage is already saturated, runoff is produced. Okay? So let's suppose, for instance, that it rains with a rain of 10 millimeters over the catchment, and this is, as I already told you, a lumped model, so rainfall is uniformly distributed. So let's suppose that over this catchment I have a rain of 10 millimeters. Rain 10 millimeters. And the question is, how much is absorbed, stored, how much is transformed into runoff? It means overland flow. So, in order to compute how much is absorbed and how much is turned into flow, I look at F 10 millimeters. So I compute F 10 millimeters. And let's suppose that this is equal to 0.2, which means that you have 20% of the catchment, like, for instance, a portion like this, which is not necessarily located here. I am just depicting 20% by assuming that is contiguous. And let's assume that it's here. So the conclusion is that with this rain of 10 millimeters, I have a portion of 20% of the catchment that is saturated. Okay, this means that next rainfall, if I have another rainfall subsequent to that one, will be transformed into runoff into this area and will be stored into this other area. Okay? Of course you may tell me, yes, but while you get 10 millimeters, you start with a portion of saturated area that is lower than that, and then during these 10 millimeters you get to this stage. So, I mean, it's clear that if I have a rain of 10 millimeters, which occurs into 1 hour, for instance, I have a dynamic change of this saturated area while it rains. So it means that I have a continuous change of this situation. It's not just step by step. And this means that, you know, we need to move forward with small steps if it's possible, because this is a finite difference approach. So I move forward step by step, and I assume that within each step the situation is static, while this is not true. In a catchment you have a continuous evolution. But of course, if we move forward with small steps like minutes or hours, that's fine. It's an approximation that you can accept. Okay, in view also of the uncertainties that we have. So I hope that I clarified in this way the philosophy of the model. The model moves forward step by step, computes the part of catchment that is saturated, and then when it rains over saturated area, it is transformed into runoff. And then there are other subsequent transformations, because of course runoff doesn't mean river flow at the closure of the catchment. Runoff needs to be propagated. So there are other pieces of the model that will propagate this runoff to the closure. But I hope that I clarified in this way, in this very simple way, how the model moves forward and what is the basic concept. You know, this is a model that is not easy to explain. You will see that it's very simple. The application is very simple. If we finish to explain this model today, I will ask you on Thursday to bring your PC, and you will see that the application is really 10 lines of program. And this is the nice and exciting feature of this model. It's indeed based on a concept that is very articulated. It's not very easy to explain, but at the end of the story, the model is very simple. So I think it was really a very good idea. It was proposed, this model, in 2000, so it's relatively young. All hydrological models are relatively young, by the way. Okay, so, of course, what you need is a way to compute this probability, this frequency. So now I have to move forward by introducing an analytical form of this formulation of this probability. Okay, let's see what is the formulation of Fc star that is proposed by IMOD, which is written, by the way, in this slide here. But look at the blackboard, I am writing it here. Fc star is equal to 1 minus C star divided C max to the power of beta k. Let me see if the symbols are correct. Yes, it's perfect. And C star is varying between 0 and C max. C max is the maximum storage into the catchment, which also is included here. So let's see what happens if I have, first of all, let me draw a graph of Fc star depending on C star. I want to draw it here, and of course C star is varying between 0 and, it's written there, C max, and Fc star is varying between 0 and 1. Of course, you easily understand that Fc max is 1. Because remember what is F? It's the percentage, the proportion, the part of the catchment between 0 and 1 that has a potential storage that is lower than a given value. So if you take as a given value the max, of course, all the catchment has a storage that is lower than C max. So Fc max is 1. Now the question also, F0 is 0, so your function starts from here. Now the question is, how is the progress of Fc star between 0 and C max? And let's just analyze this function for different value of beta k. Let's suppose that beta k is 1. If beta k is 1, here easily you understand that you have a straight line connecting 0 with the origin with C max 1. Okay, because if beta k is 1, of course you have 1 minus 1, which eliminate each other, and then plus C star divided C max. It's a linear function, and this is beta k equal 1. It's written here, and what I'm telling now is written here and in the web page. Okay, now let's suppose that beta k is let's see another extreme is tending to 0. Okay? And what happens if beta k is tending to 0? You reduce to f c star tending to 1 because, oh sorry, tending to 0. And therefore it means that for increasing value, and the reason is that a number to the power of 0 is 1, 1 minus 1 is 0. So this means that you have a behavior like this. It's 0 everywhere, and suddenly it gets to 1 when you get to Cmax. Of course, this is a limiting tendency, and actually you will have something like this if you are very close to 0, and then a sharp increase here. What does this mean? It means that you have a storage that is constant over the catchment, and it's equal to Cmax. Because it means that for increasing C star, you have a proportion of the catchment with lower storage with respect to C star that is 0. It means that everywhere is higher, and then when you get to Cmax, you get everywhere storage equal to Cmax. So this is similar to the linear reservoir. The linear reservoir assumes that you have a storage into the catchment at a given time that is uniformly distributed over the catchment. And therefore, if you have rain over this catchment, what happens? It happens that the rain is absorbed until the soil has absorbed the value of Cmax. And then the next rain will produce runoff over the whole catchment. This is what happens. Okay, and what happens if beta k tends to infinity? If beta k tends to infinity, you have the opposite situation. Something like this. In fact, here, if you have, what you have here is something that is lower than 1. This parenthesis, this round parenthesis, includes something that is lower than 1. Because C star is lower than Cmax, positive, and therefore you have 1 minus something that tends to 1. And therefore, this is lower than 1. To the power of infinity, it means that it goes to 0, and therefore Fc star is 1 everywhere. Which means that the proportion of the catchment that has a storage lower than C star is very high, which means that the catchment doesn't absorb much water, and therefore the curve is something like this. Of course, you expect that Cmax in these conditions is reduced. Okay. Now, let's see an interpretation of this curve. Let me draw this graph here. I draw it bigger. Oops, sorry. Okay, this is Cmax. I'm just redrawing the graph, and this is 1. And let's suppose that we have a progress like this, which means that beta k is higher than 1, and but of course well lower than infinity. Okay. Now let's move forward by assuming that it starts raining over the catchment. Let's see what happens over the catchment when it starts raining. And let's assume that we have a rainfall event which starts with a rainfall event that continues in time. So it keeps raining. And let's suppose that we don't have any reduction of storage into the catchment due to, for instance, evaporation. So everything that rains is absorbed into the catchment and kept there. This is an ideal situation. Actually, we have some processes that tend to reduce the storage into the catchment, the storage in the soil, and basically it's evaporation and transpiration and water losses. But let's forget them for now. We will keep them into account later. Now, let's forget this, and therefore what happens is that it rains over the catchment, uniform rain, and the catchment starts absorbing water. And this water that is absorbed is conserved. Now, let's define with the variable Ct. C, you understand, it's a storage. What is Ct? Ct is the storage at time t. And storage at time t, because given that it rains over time, I have in the catchment, in some locations, a storage that increases with time. And this Ct, let's define it as the storage in the area of the catchment that are not saturated. So it's lower than Cmax. So look at the catchment as a sponge, and a sponge with a heterogeneous capacity to absorb, and where you have the sponge that is not saturated, you indicate the storage as Ct. You understand that this Ct is equivalent to the rain from the beginning of the event. Okay, so it starts raining, and where the catchment is not saturated, everything that rains is absorbed. So this is a storage that is increasing in time, dynamically, depending on time. Of course, it increases in time up to saturation. So let's assume that it indicates storage where we don't have saturation. Okay? Of course, we can depict Ct over this graph. It's a storage, so I can depict it here. And so I can, for instance, take this value of Ct, and this is, Fct, and this is Ct. Like it's done here, Ct, Fct here. Okay, of course you are at a certain time t, so you are at a certain time t during a rainfall event. Now, what happens if I have a subsequent rainfall, like you see in this figure? Let's assume that I have a subsequent rainfall here. Okay? If I have a subsequent rainfall, I move forward to Ct plus delta t. Okay, there you see the t, that's equivalent, the same thing. And here I have a F Ct plus delta t. when you move from Ct to Ct plus delta T, you add a rainfall over the catchment. Storage is increased because you add a rainfall. But part of this rainfall is stored, part of this rainfall is converted into runoff. My question is, what is the part of the rainfall that is stored? What is the part of the rainfall that is converted into runoff? Your rainfall is given by this rectangular area. This is your rainfall over the catchment. Okay, and I see this overall rectangular area because rainfall is over the whole catchment, which means 1. So I have to extend this area up to 1, because the proportion of the catchment over which it's it rains, it's 1. So this is my rainfall from T to T plus delta T. Now, again, my question is, what is the part of rainfall that is stored? What is the part of rainfall that is converted into runoff? And so let's look at this area, which is split into 2 parts, as you see here. There is a part below the curve, the progress of the curve of the model, and the part above the curve. Okay, so what is again, what is storage and what is runoff? Now, what is the area that is below the curve? The area that is below the curve, let's suppose that this delta T is very small. So let's assume that you can obtain this area by multiplying rainfall at time from time T to time T plus delta T. You can multiply rainfall by FCT, which is here, okay? Of course, you may say you are missing this part, but again, let's suppose that the interval is very small, so this part that we are missing is very, very reduced, okay? So what this product here, what is? It's rainfall times the part of the catchment that is saturated. Because again, your proportion, your function f gives to you the part of the catchment that is a storage lower than Ct. So this is rainfall, again, times the part of the catchment that is saturated. Okay, so this is surface runoff. It's rainfall over the saturated catchment. So you see what's written here, contribution to runoff. What's above is the complement to 1, which is contribution to storage. This is very nice to see. What does it mean? It means that if I integrate the function fc star between, for instance, time t and time t plus delta t, the integral of the function fc star is the contribution to runoff. You know that the integral of a curve gives to you the area below the curve, and therefore, again, the integral of the function fc star is the contribution to runoff. The complement to 1, the complement to rainfall, is contribution to storage. So, what did I learn here? I learned that in order to compute during a rainfall event what is runoff and what is storage, I need to compute the integral of the curve. So, from time 0, when I observe a rainfall, up to time t, end of rainfall, if I compute the integral of the curve, I get the surface runoff over the catchment, which then has to be propagated to the closure, but this is something that we will see later. And don't forget that we excluded any losses, any water loss. We have to consider also water losses. We will see later. But now let me compute the integral of the curve. And you understand that if the guy who invented this model, the person who invented this model, was smart enough, probably he tried to conceive a function describing fc star that is easy to be integrated analytically. In fact, we will see that this function is easy to integrate analytically, and then you understand why this particular form of the function. Because she wanted to propose a formulation that is easy to handle mathematically. Then we integrate numerically, but 20 years ago, numerical integration was not as usual as it is now. It was already quite well used, but they anyway wanted to make the problem tractable. Okay, let's then compute this integral. And this is something that I usually like to ask at the exam, the computation of this integral. And what we need is to compute the integral between 0 and t of f. Let me use the same symbols, just 1 second. F tau in the tau, okay. F key in the key. Where, because I needed to introduce a variable of integration, so I'm not using again c. And the integral, sorry, is to be computed from 0 and c tau. And ct, sorry. Yeah, symbols are okay. So this is the integral, I write it explicitly, between 0 and ct of 1 minus key divided by c max to the power of beta k in the key. By the way, this is an animated figure that you see on my web pages, which explains the progress. So you have this curve, and then it starts raining, and you see the progress. It may continue to rain after Cmax, which means that if it continues to rain, what rains above saturation is simply transformed directly. Everything is transformed into runoff. Okay, so I have this integral. So the steps of integration that I'm writing now on the blackboard are reported on my web pages, so everything is there. And let's move forward. So this integral is equal to, okay, first we have the integral of 1, because this is an additive integral. So first I have the integral of 1 in the key, and therefore this is equivalent to key computed between 0 and ct. Okay, minus, and then I have the integral of, I'm just copying, between 0 and ct of 1 minus e divided c max in the key. Okay, so equal to, okay, this one is equal to ct minus ct because I substitute the extreme of integration minus. Okay, this is, I would say that this is equivalent to C max divided beta k plus 1, which multiplies 1 minus k divided C max to the power of beta k plus 1. And this is computed between 0 and Ct. Okay, now let's try to understand what I wrote is correct. This is the integral of an exponential function. I forgot here, sorry, to write beta k, the exponent. I forgot the exponent there. So let's see if I get, by computing the derivative of this quantity here between square parentheses, let's see if I get the argument of the integral. This is the derivative of an exponential, so what I get here is the beta k plus 1, which multiplies the argument of the exponential to the exponent minus 1 times the derivative of the argument of the exponential, which is minus C max. So I would say that everything is probably correct with the exception of a minus sign, because I have a minus sign here, so I think I have to put a plus here. Okay, let me check if everything is correct, and then let's just 1 second. I'm looking at what it's written there. Yeah, it's correct. Okay, now I have to substitute the extreme of integration. Let me go here. So this is equal to Ct